Hey guys, so first announcement, I'm going to be changing my name from GreatGamer34 to The Wild Drive-Eye because I think GreatGamer34 is just like a super generic, really like stupid like username. Like I made that when I was really young. So I'm going to be moving away from that first of all. Second of all, I want to show you this BYTE Addressable RAM that I made in LOGISIM with thanks to the CS3410 library that you're able to download. So in here you have this little thing called MIPS RAM, and if I drag it out, it's just the RAM block, but the select thing here gives you a way to address the individual bytes within the word. And so taking advantage of that, I built this, which allows you to store data either as a byte, a half, or a word. In this case, a word is 32 bits, so a half would then be 16, and then a byte is obviously 8. And then, so you can do a signed load or an unsigned load. So I'm going to give you an example of what this does. Okay, so in this example that I want to do, in the byte, I want to have something that's going to end with a 1, so that it'll be sign extended when we read it, when we want to do a signed load. So to do this, we're going to put an F, or an F here, and then I want to do the same thing for the half, when we load a half. So I'm going to put, I don't know, maybe an E here. So that's the first priorities, and then so I guess I'll put in like a 3 here. I'll put in a 5 here. I'll put in an 8 here. I don't know, maybe 7 here. And then we'll go 8, 9, like that. Oops. Okay, so we got some data in. So the first thing I want to do is I want to write a byte to byte address 1. So the addressing modes go 0, 0 is not going to address anything. 0, 1 is going to address as byte. 1, 0 is going to address as a half, and 1, 1 is going to address as the whole word. So we want to store as a byte. We're going to click store, and we're going to store this lower byte here to byte address 1. So if I clock it, we now have this value right here stored into byte address 1. So if I do a unsigned load, rip. Alright, let me investigate. Okay, so when I click unsigned load here, you see that we get the bottom 8 bits of the data in that I wrote, because I wrote that byte to the byte address number 1. You'll see here if I stop reading that address, we don't get it. So let's see what happens if I go to a signed load. Well, you'll see because the last bit here was true, we want to carry that bit throughout all the rest, and we get our signed load like that, so we can preserve our sign. Okay, that's cool. Now let's go to byte address 5, and instead of storing a byte in 5, actually we're going to go to 4. Actually, no, we'll go to 4 instead. And what we'll do is we'll write a half. So when we write a half, we put it in that addressing mode. Now it's going to store the bottom. I'll select them with this. It's going to store these bits here, the bottom ones. So because the topmost bit of the 16-bit word, or which is technically a half a word, right? The 16-bit half is true. When we sign extend it, all the rest should be true also. So let's write this to address 4. So if I store it and clock it, now I can do an unsigned load and we get that value. Or I can do a signed load and we get that value. Then we can still go back and read address 1 and unsigned load or signed load it, whatever. It's 24 bits of addressing, which is 16 million numbers that this can hold. 16 million 32-bit values. Which is a lot of values. Anyway, so now let's go to addressing mode of a word. And so now we basically have to be aligned on a byte boundary, which basically means these 2 bits cannot be true. You have to be writing somewhere in here like this. So you have to be in a word boundary to be writing a word or reading a word, basically. So we already wrote to 4, so we'll write to 8 instead, maybe. And then so if we write to 8, oh, the other thing we can do is write to 0. But when we write to 0 is so we have a 1, we have a byte in the value, in the byte 1, right? Oh, I'm doing the wrong address. There we go. Yeah. So we have a byte in that value. If I try to read a word from there, you'll see it actually reads the word it aligns on the byte address. So even though we're entering byte address 1, it's aligned at byte address 0 to 3 because that's where the word resides. So you can do a lot with this format like this, allowing you to manipulate where the byte and whatnot is held. And anyway, so the main point I want to show you here now is if we write a word, so I'll go somewhere else that won't overwrite, so we'll go to 8 instead. I won't do that, and if I clock, whoops, I have to be storing. So if I clock this in, then do an unsigned load. Oops, I'm trying to store stuff. Okay, one more check. Clock. Good. No, let's see what's going on. So it's a simple error here with this transistor, so I had to use the mux, so I'm going to fix it right now. Okay, so now, if I do an unsigned load, it should work. Oh, it shouldn't be storing. Let's try it again. There we go. Okay, so ta-da, it works. Alright, it was a transistor that I had to change to a mux because for some reason the transistor went floating or error state instead. So now you see that on the byte boundary we stored this, but now let's see what happens if we don't store it on a byte boundary. Alright, so if I stop loading, and let's say I overwrite this to, actually we'll go back to, we'll increment from 8, we'll go to 12 like that, the next 4 byte boundary. And then what we'll do is we'll try to offset it by 1 and see what happens when we write a byte, or when we write a word. So when we write a word, offset by 1, you'd think that this lowest byte right here would be offset by 1. But what's actually going to happen is the whole word is going to write as if it's ignoring whatever the hell you wrote here in these. It's just going to take the advice of these 2 bits, of the most significant bits, past these least 2 significant bits. Because the way this works is it's byte addressable, and since each word consists of 4 bytes, 0, 0, 0, 1, 1, 0, and 1, 1 are ways to address a byte within a word. And since we're writing a whole word, we ignore those least significant bits. So watch what happens. So we're in addressing mode of writing a word. If I go to store this and I clock it, and let's see what happens when I read this. You'll see that I get the whole thing out like this. It's not shifted up by 1 with zeros filled in the bottom row. So you have word addressing and you have byte addressing also. And then, of course, the signed load is the same as the unsigned load. It doesn't matter because it's a whole word. There's nowhere else to fit. You can't fill in any ones if the most significant bit is 1 in a 32-bit word if your whole word is 32 bits, right? All right. And so yeah, that's the end of this video. I just wanted to show you this, and I will leave a link for this in the download, or in the description, along with the CS240, or CS3410, sorry, component. And I can show you what they are real quick if I go to main. Oh, no. If I go to add circuit, new. So CS3410, you get the MIPS RAM, which just gives you this to be able to be multi-bits instead of just 1 bit, like in the normal RAM. It functions basically the exact same way though, like this, but this select bit is a single bit, and the select bit is multiple bits. Okay. You have program ROM, which I would never use. You have register file, which is useful, I guess, if you want to use it. It's interesting. You have an ALU here that you can just use for whatever you want it to do. It's a MIPS ALU. You have an incrementer, which is useful. And then you have this thing, which is super cool, but is going to require a lot of work to use. You have like RGB, and it's a colored LCD screen that you can actually do stuff with in LOGISIM. So my goal is to eventually build a CPU that's going to be able to run something cool on this. But first I want to just get monochrome working, and then we'll try to go for color. But yeah, so there's a lot of stuff in this. So in the download, I'll leave you the CS3410 components, and then I'll leave you my library also. All you have to do is when you start LOGISIM, you go up into Project, Load Library, LOGISIM Library. You go to wherever you downloaded my file, and you load that. Well, actually, before you download my file, whoops, you have to go to Project, Load Library, Jar Library. This is where you have to get the CS3410. You open it, and then it loads in all of your components right here. And then if you go to Project, Load Library, LOGISIM Library, and you pick on the byte address RAM that I'm going to give you, and you open it up, then you'll have everything in here, and then you can just go right in and use it however you want. I wouldn't suggest going inside and seeing how it works because it's a mess of wires. Here's what it is. So address comes in here, data's here, and then control logic is kind of down here with some like more control logic built in all around, right? So basically what has to happen is I have to figure out what type of value I'm writing, and then the type of value I'm writing determines how I'm going to parse the input to be where I need it to be in the bytes. And you can see here's the RAM actually, whoops, I don't want to do that, Control Z. You can see there's the RAM, zoom in on it, which actually shows you, whoops, which actually shows you the values held inside of it like this. So you can see how we're able to manipulate values and whatnot. And then the muxes here are all meant for reading, and then this is how I do the sign extension right here. I can either sign extend or zero extend, sign extend or zero extend, and then pick which one I'm doing with the mux. The issues I was running into before when it wasn't working oddly was, oh, wait, I just realized that you guys can't see. Let me move over. Shoot, I can't. My screen is too wide for this recording software. Yeah, let me figure this out. Maybe. There we go. There. So, you can see I have the sign extend and the zero extend here, up the mux, and then I can pick which one I want to read also. So the mux out of here basically does the combination logic that I need to combine certain bits. Just like, so I had to do the carry logic here that said when I'm reading a byte, or when I'm reading a half, the half doesn't have to be aligned on a 4-byte address. It can be anywhere in there, and you can read any of them. But obviously the topmost one won't work. You can't read a half when you're at the top already because there's no way to read the next byte above that. So it doesn't work there, but it works for this one, and this one like that. And that's why the carry logic is arranged like that. And then you can see that carry logic is then accomplished on the output by using the splitter and splitting it up like that. But anyway, I'm sure if you guys play with it, you could figure out how I built it here and probably clean up this wiring and make it probably more efficient or something like that. And then the other thing that I guess is important to show is right over here. So the address comes in, and we have something that shifts it down by 2, so it ignores those first 2 bits, and then uses that as the address because it stores a word, right? And then it takes those low 2 bits right here, bit 0 and 1, off that splitter, so if I zoom in, takes bit 0 and 1 off the splitter and ignores the rest of the bits and then puts those into a decoder. So a 2-bit decoder has 4 outputs, and then so it determines where the select, because the select bit is 4 bits, because it's able to store either 1, 2, 3, or 4. You pick which. The way it works is it's 4 bits and they have to be consecutive lining up from the bottom. So you can either store to 0, you can store a byte to 0, 1, 2, or 3. You can store a half to either 0, 1, 1, 2, 2, 3, or you can store a word to 0, 1, 2, and 3. Like that. So that's the way this is set up. And so that's why this carry logic is done like this and it's ordered like this for all the different things. And then I tied a 0 just in case anything wants to bug. And so far it's worked for me, except for when it hasn't because I was trying to change these muxes to transistors. So long story short, stay with muxes and you're good. And thanks for watching. I'll see you guys next time.